So good morning, everyone, and welcome to this lecture. This is lecture number 6, and we are going to deal and finish with Ampere's law in this particular session. If you remember, in the last class, we had seen the particular cases where you can use Ampere's law to find out the magnetic field. We had seen we can use Ampere's law to find out the magnetic field of an infinite wire mu naught I by 2 pi r. Do we remember this? We have seen this formula before also. We saw it once again. Then we saw due to a hollow cylindrical wire, this is the magnetic field. Inside it is 0. On the surface mu naught I by 2 pi capital R. Outside it is mu naught I by 2 pi small r. The maximum field is on the circumference or the surface. Do we remember this? Yes or no? Remember this? Yes or no?
Yes, sir.
If we have a solid cylinder, solid wire, then the magnetic field inside is directly proportional to R. At the center it is 0. On the axis center point it is 0. It is maximum on the circumference. Then we saw these three revolutionary diagrams where we saw everything put together. Yes or no?
Yes,
Remember
sir.
this? Now I will again show you a table where you have for the solid cylinder, hollow cylinder. We have already seen that inside it is 0 and outside it is mu naught I by 2 pi r. This is a snapshot of. First, let me explain. Then I shall give you enough time to write it. Now you will see two types of cylinders here. One is a solid cylinder, it's completely solid. One is a thick cylinder which has got inner and outer radius R1 and R2. We all of us see this, yes or no? So you can
Yes,
see
sir.
what is important is just the final line. The final line is here. You don't have to remember the initial line. You just have to draw the diagrams and you have to remember this final. Inside, at any point, the magnetic field is mu naught I R upon 2 pi into capital R square. Outside any point, it is how much? Magnetic field outside is how much? Mu naught I
Mu
by
naught I by 2 pi r.
small r, where r is the distance from the axis of the cylinder. If you have a thick shell, you don't have to remember anything apart from this thing which I am going to put in a box. This is the magnetic field in between the cylindrical shell. Do you see this region? Yes or no? Huh?
Yes, sir.
Inside the magnetic field is 0. Remember here inside this part magnetic field is 0. Also on the inner surface, the magnetic field is 0. You just have to write the points which I am highlighting. On the outer surface, the magnetic field is mu naught I by 2 pi r2, where r2 is the radius of the outer part. And if the point is even outside this, the magnetic field will be how much? If the point is outside, not on the surface but outside, yes?
Mu naught I by 2 pi capital R.
Mu naught I by 2 pi small r or capital R, whatever you call it, where small r is the distance from the axis of the cylinder. Do we understand this? Yes or no? No, yes.
Yes, sir.
I'll give you a minute to note it down. Well, then, this is the question that I'm giving you. You have a solid cylinder, infinite solid cylinder, or some people may call it solid cable. Infinite solid cable. This cable carries a current I. The radius of the cable is R, capital R. You have to find out the magnetic field at the point which is shown. The distance of this point from the axis of the cylinder is r by 2. So this distance is given as small r. The value of this small r is r by 2. I'll give you a minute to give me the answer for this one. So what is the answer for this one? Anyone got it? The formula we have to apply is mu naught I into small r divided by 2 pi into capital R square. You just need to put the values. So what are the values? Mu naught, current is capital I, small r is r by 2 divided by 2 pi into r square. So the final answer will be mu naught into I by 4 pi r. Do we understand this? How I've got this result? Yes or no? I just put the
Yes,
formula
sir.
of solid cylinder inside and then I got the value. I've got one more question for you. Do it fast so that I can move ahead. This is the next question that comes on your screen now. Figure shows the cross-sectional view of a thick cylinder. The inside radius is r, outside radius is 2r. You have to find the magnetic field at a distance 3r by 2. I'll give you 2 minutes to give me the answer for this one.
Sir, option D.
Option D is correct option. Well done. So what we got to do here, bacha? We just have to apply the formula B is equal to mu naught I by 2 pi small r into r square minus smaller radius divided by bigger radius square minus small radius square. Do we remember this formula?
Yes, sir.
That's it. We just need to apply it in this formula. B will be equal to mu naught I by 2 pi. The value of the small r is 3 by 2r into the value of the small r is 3 by 2r. I square it. 9r square by 4 minus small radius is r square divided by 2r square is 4r square minus r square. It might take some time for you to calculate it, but if you calculate it correctly and patiently, you should get up this answer 5 by 36 mu naught I by pi r. Do we understand this? Yes or no? No, yes.
Yes, sir.
Everyone understands this?
Yes, sir.
Pakka, sir.
Pakka, sir.
Then we come to the next heading, magnetic field due to infinite sheet. Magnetic field due to infinite sheet. Now, what do I mean when I say infinite sheet, bacha? Infinite sheet means a sheet which is infinite in length and infinite in breadth. So that means this edge is not ending. This edge is going till infinity. This edge is going till infinity. This edge is going till infinity. And this edge is also coming or going till infinity. Do we understand the meaning of infinite sheet, beta? This is also the same as the infinite sheet of charge. Infinite in this dimension, infinite in this dimension. Do we understand this? Yes or no?
Yes, sir.
We have a point P which is here. So sheet is kept like this. Point P is here. Do we understand this?
Yes, sir.
As you can see this sheet carries current in this direction. Now this answer that we are going to write will not be in the form of the current, it will be in the form of lambda, which is current per unit length. If I call the length of the sheet as L, it is very large, but let me call it as L. This lambda is the current per unit length. Current divided by length. Do we understand this? Now,
Yes, sir.
if I find the formula of this magnetic field, the formula will come like this: mu naught lambda by 2. Mu naught lambda by 2. And if you remember, this is similar to formula of an infinite sheet. Do we remember this infinite sheet which had a charge density of plus sigma? We had found out the field at point P. The electric field at point P was sigma by 2 epsilon naught. This formula is exactly similar. 2 comes in the numerator, 2 comes in the numerator. Epsilon was in the denominator. Here mu naught is in the numerator. There it was sigma. Here it is lambda, current per unit length. Do we understand this?
Yes, sir.
This is the magnetic field due to a infinite sheet. Now, how do I find the direction of current, direction of field? So you can see magnetic current is going like this. Point P is on the top. So current is like this. Thumb goes in the direction of current. Palm goes in the direction of the point P. And I rotate my finger. Do we understand? So direction of magnetic field will be like this. Do we understand this? So the direction of magnetic field will be like this. Anyone understands this? This is current. Current is going like this. Point P is on the top. The magnetic field goes in the rightward direction. Do we see this? Yes or no?
Yes, sir. Yes, sir.
Mu naught lambda by 2 is the answer. I shall give you a minute to note down this.
I thought you didn't draw. You said you don't know how to draw. That's why I thought and show you how beautiful I'll draw. It's beautiful, no, right? Ah, only Manaka? Or observed at the notes in Naga. Or okay? That is the last class, no? Done, sir.
Everyone done, sir? Okay, sir. Then we move ahead to the next thing, sir. This is magnetic field due to toroid. What is a toroid? What is toroid? Toroid is this gentleman. Which gentleman? And I shall show you the picture of the toroid. Now, once upon a time, there used to be a bike and car tires, and those tires used to have tubes made up of rubber. Nowadays, they are all tubeless. Tire tube of a tire, and this is a tube of a tire. So it's a ring-shaped solenoid. Do we understand this? Huh? Ring-shaped solenoid.
Yes, sir.
What, sir?
It's a ring-shaped solenoid.
It's a ring-shaped solenoid. So basically, what I have done, I've taken a long straight solenoid and ding. I've done this ding. Do you understand ding?
Yes,
So
sir.
this becomes a toroid, my dear friends. As you can see, the current in the toroid is N, and this green thing is the axis of the solenoid, which now becomes the axis of the toroid. We understand this, yes or no? Huh?
Yes, sir.
This is outside the solenoid, so magnetic field here is 0. This is also outside the solenoid, magnetic field is 0. Remember, in the previous question, I forgot to tell you, outside the solenoid, the magnetic field is taken as 0. So write it. Outside the solenoid, the magnetic field is always taken as 0. Same concept has been applied here. Outside the solenoid, which now becomes a ring-shaped toroid, magnetic field is 0. You can only find the magnetic field at the point on the axis, which is at a distance r. And the value is mu naught n. What is n? N is the total number of turns. You can see mu naught n I by 2 pi. Sorry, mu naught into n I by 2 pi r. Why did I? Or you can write this as, if you want to write it similar to the field of a solenoid, you can still write it as mu naught ni, where n again becomes the number of turns per unit length. 2 pi r is the length of this solenoid. Yes or no? No, yes. Do you understand this? Or it has gone above what it's saying bye bye, sir. I'm going bye bye. Bye bye. Bye bye. Bye bye. Huh? If you understand this, you have 1 minute to note it down fast. Then comes a very small question, sir. Two solenoids having length L and capital 2L, and the number of loops N and 4N have the same current. What is the ratio of magnetic field? You have 2 minutes to show your talents. Option A is the correct option, my dear friends. We must remember that magnetic field due to a solenoid, infinite solenoid, is mu naught I by mu naught Ni by L. I can see that magnetic field is directly proportional to the ratio of N and L. So B1 by B2 will be equal to N1 by N2 into L2 by L1. N1 by N2. N1 by N2 will be 1 by 4. L2 by L1 would be, I think, 2:1. So I get the answer is 1:2. I am very bad with ratios, but I hope I have corrected this. I have done it correctly, and the answer, it seems, is option A. Do we understand this? Yes or no? No, yes. Everyone got this? Okay. One more question, the last question in this category, and I hope that my kids can do this. This is the one. I'll give you 2 minutes to give me the answer for this one. So, bacha, how are we supposed to do this? We know that magnetic field is mu naught into N into I. Here N is the number of turns per unit length. It is given as 20 turns per centimeter. But remember, we have to find it in SI units. So it will be number of turns per meter. Per meter. That is why this question was given. So number of turns per meter will be 2000. Do we understand this? 2000 turns will be there per meter. Do we understand this? Yes or no? Yes or no?
Yes,
So
sir.
the value of magnetic field is given. Value of magnetic field is given. Magnetic field is 20 millitesla. So 20 into 10 raised to the power minus 3 millitesla will be equal to mu naught. And mu naught will be 4 pi into 10 raised to the power minus 7. 10 raised to the power of minus 7 multiplied by number of turns is 2000 multiplied by the current is I. When you calculate this, you will get the required answer of I. I will be equal to 20 into 10 raised to the power minus 3 divided by 2000 into 4 pi into 10 raised to the power of minus 7. Do we understand this, everyone? So what we have to remember from this, if the turns are given per centimeter, convert them into turns per meter multiplied by 100. Do we understand this? Do we understand this? Okay, with this we come to an end of this session and this class. In this class, we had seen the Ampere's law. In the next class, we shall begin with the next part, which is the magnetic force. I'll try to wind it up as soon as possible. In the next class, we'll deal with magnetic force. Take care. God bless you. Bye-bye.